a sequence is really just a list of numbers. And generally we're going to show this in kind of a set formation. So there is a sequence that has 3 terms in it. Now this is called a finite sequence because, well, it has a finite number of elements in it. We can also have infinite sequences that go on forever, and of course we use the dot, 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 which are called ellipses, to show that that continues going on forever. So we have a finite sequence and an infinite sequence. Now most of the time when we have an infinite sequence, instead of trying to write it all out, we use what's called a generating formula or an nth term formula. So this is going to be a generating or nth term formula. Now the way that we're going to do this is we generally say that some a sub n is given by some function of n. Now what do we mean by that? Well, it means this is just going to be some function that has n's in it, and it's going to tell us what every a sub n is. Now in here, n is our index, and that's going to run from 1, 2, 3, so on. So this would generate the sequence. When we plug 1 in there, that would be A1, A2, A3, so on and so forth. So let's do a quick example. So let's say I gave you the generating formula or the nth term formula of n squared plus 1. And I said, let's do the, write the first 5 terms. Okay, so for our first 5 terms, all we would do, we just start plugging in values. So a sub 1 would be 1 squared plus 1, which would be 2. A sub 2 would be 2 squared plus 1, which would be 4, 5. A sub 3 would be 3 squared plus 1, which is 9, 10. A sub 4, 4 squared plus 1, 16 plus 1 is 17. Let's do one more to get to our 5th one, so that's 5 squared plus 1, which would be 26. Now, of course, if we wanted more terms, we could continue to plug them in. So if we wanted to write out the first 5 terms of this sequence, what would it be? 2, 5, 10, 17, 26. And then doing the dot, dot, dot says that, well, this pattern is going to keep going on forever. Now, the nice thing about having the generating formula or the nth term formula is you don't have to go in order to list them all out. I could say, what would the 10th term be? So you could ask, what would the 10th term be? Well, the good news with something like this, if we have a generating formula or the nth term formula, all we're looking for then would be a sub 10, 10 squared plus 1, which would be 101. So you can find any term in a sequence if you have the generating formula or the nth term formula. All right, so a sequence is just a list of numbers that is generally given by our a sub n's, and notice that our a sub n was just some function of n. Now there's another way that we can represent sequences, and this is called a recursive formula. Now these are a little bit more tricky. A recursive formula, you can't go from any term that you want to, like you can't jump to a sub 10, because the one that you're looking for, let's say we're looking for a sub 4, is going to depend on some of the values that came before it. So something like this would be a recursive formula. A sub n is equal to 2 times a sub n minus 1 plus 3. So notice, whatever one we're looking for, like if we're looking for a sub 4, this would be based off of a sub 4 minus 1, so a sub 3, so one that came before it. Now if you notice, this kind of has like an infinite regression backwards though, right? If I want to know a sub 4, I need to know about a sub 3, which means if I need to know about a sub 3, I need to know about a sub 2, and it would keep going backwards forever if we don't have a starting point. So with a recursive formula, you have to have some type of beginning information. So you'd be giving a generating formula, and you also have to be given some values, some starting points. So let's just say a sub 1 was 1. So just to kind of show you how this is going to work, I'm just going to run off a few of these. so you can see how a recursive formula works. So we already know what a sub 1 is, so we'd actually start at a sub 2. That'd be 2 times a sub, excuse me, 2 minus 1 plus 3. That's 2 times a1 plus 3. Now notice that this is referring back to a value that we know before, so we can plug that in. So that's 2 times 1 plus 3, which is 5. All right, if we wanted to know the next one, a sub 3, well, that'd be 2 times a sub 3 minus 1. That's 2a sub 2 plus 3. Now notice it refers back to the one before it. We know what a sub 2 is. We just figured that out. That was 5, so this will be 2 times 5 plus 3, which is 13. All right, I'm going to do another one more here. Let's do a sub 4. That would be 2a sub 4 minus 1 plus 3. That's 2a sub 3 plus 3. Well, we know a sub 3 from the last one, that's 13, so 2 13s plus 3 should be what, 29, right? 26 and 3 is 29. All right, and we could keep going forever. Now, here's the problem with these. I can't do this right away. I can't say, what's a sub 10? Right? Like we could with our last one, we could just jump to any value we want. To find a sub 10, I have to find all the values before it. That is one of the problems with our recursive formulas. Now, there is one recursive formula that I kind of have to mention here. It's a very, very important one. Let's see if I said a sub n is equal to a sub n minus 1 plus a sub n minus 2. Now notice this is a two-term recursive relationship because it refers not only to the one right before it, but the one before that as well. Now since this goes back 2 places, I actually need 2 pieces of starting information. So my 2 pieces of starting information for this specific series is generally A1 is 1 and A2 is also 1. Now if you start plugging into this, now we already know A1 and A2, let's go A sub 3. A sub 3, now here our n is 3, right? So I'm going to do this kind of quick. 3 minus 1 would be 2, 3 minus 2 would be 1. So A2 plus A1, we know what those are, 1 plus 1 is 2. A sub 4 would be, say we're plugging in for 4 here. So this is A sub 3 plus A sub 2. We know A sub 3, we just figured that out. A sub 2 is 1, so that's 3. I'm just going to do a couple more here. A sub 5, well, you can kind of see how the pattern is going to work. That's going to be 4 and 3. So A sub 4, A sub 3. So A sub 4 and A sub 3 is 3 plus 2 is equal to 5. Now you can kind of see how this is working. Let me show you one more here. A sub 6, that would be A sub 5 plus A sub 4. A sub 5 plus A sub 4, that's 5 plus 3 is 8. Notice all we're doing is we're adding the 2 that came before it. So this is actually fairly easy to write out our sequence. We go 1, 1, those were the 2 we started with. Then we have 2, 3, 5, 8, 2, 3, 5, 8. Now instead of writing all this out, we know how this pattern is going to go, right? What do? We just add the 2 previous to get the next one. So if I want the next one, I'd add 5 and 8 and we would get 13. If I want the next one, I'd add the next 2 previous. That would be 21. So on and so forth to give us our sequence. This is called the Fibonacci sequence, which I probably spelled wrong, so make sure you spell Fibonacci right in your notes. It's called the Fibonacci sequence. This is a very, very important sequence. It shows up in nature a lot. There's a whole books full of stuff that has to do with the Fibonacci sequence. If you're interested in interesting patterns that occur in nature, this is something you definitely want to look up. We just don't have the time to really go into it today. All right, so we've seen what a sequence is. A sequence is just a list of numbers that's generally given by a generating formula or an nth term formula, and it could be a direct formula like our first example or a recursive formula kind of like our Fibonacci sequence here as well. Now let's come up with a few more things about a sequence. We say that a sequence is said to converge if. All right, here's the idea for whether or not a sequence converges or diverges. Kind of like when we did our improper integrals, we had the idea of what converge and diverge mean there, right? For our improper integrals, converge means that it summed up to a finite number. Diverge means it summed up to infinity. Kind of the same idea here. Here, if we take a look at this list of numbers, where does it look like this list of numbers is heading to, right? This is actually heading towards infinity. So that's not heading towards a specific value. So we would actually say that this sequence diverges, right? It heads off to infinity. What if we had this sequence here? This is an easy one. 1/2, 1/4, 1/8, 1/16, 1/32. What's happening with this? Well, as you see, it's going down by a power of 2 each time, right? So this is getting smaller and smaller and smaller. You can see that's heading towards a value of 0, right? Eventually, this is going to get so small, it's basically going to be 0. So this is heading towards a value. So we would say that this sequence here converges, and it converges to the value of 0. So how do we determine whether or not a sequence converges or diverges? If, let's say that we have our a sub n is some f of n, right? That our a sub n is some function of n. If the limit as x goes to infinity of f of x is equal to L, and I'll describe what L is to be, let's go ahead and do that. So if we think about this instead of terms of n being an integer, right over here, n had to be 1, 2, 3, 4, but if we think about it as in terms of a continuous variable, just x, any x, if that limit goes to a value that falls between negative infinity and infinity, it converges. If that's true, then the limit as n goes to infinity of a sub n is also that value L. So, a sub n converge. Okay, so let's see if we can understand how I have this written. It says the sequence said to converge if we have a sub n some function of n. Well, if the limit as x goes to infinity, because we need a continuous variable here to do the limit, is equal to L, then the limit as n goes to infinity of that sequence will also go to L. As long as L falls between negative infinity and positive infinity, we say that the sequence, and these are curly brackets, some really crappy curly brackets, this is generally how we show a sequence, then the sequence a sub n will converge. So what does it mean to diverge? Well, if L goes to either positive or negative infinity, it diverges. Okay, so this is all fairly simple as long as we know how to do limits as we head towards infinity. Now, L'Hopital's rule is going to come into play here quite a bit as well, so let's determine if the sequence converges or diverges. Well, let's say that a sub n is equal to n over n squared plus 1. Now here's the great news. We actually don't need to write out terms in this sequence to determine whether or not this sequence converges or diverges. Really all we have to do is we have to take a look at the limit as x goes to infinity of x over x squared plus 1. Well, if we try to do this, we can see that this is infinity over infinity, so we can say this is equal by L'Hopital's. See, L'Hopital's only works on a continuous variable here generally, so we want to, that's why we switched over to x's. By L'Hopital's rule, the derivative at the top over the derivative of the bottom, well, that's 1 over infinity, which is 0. So that means the limit as n goes to infinity of n over n squared plus 1 is also 0. Since this is a value between negative infinity and positive infinity, we say that a sub n converges. All right, let's try another one. Do one more here. What if I said a sub n is equal to I don't know, negative 1 to the n plus n all over 3n. All right, so if we wanted to do this, let's just take a look at the limit as, now we could go to x's here, and this is what a textbook's normally gonna do, but really we're just looking at, as n goes to infinity, of negative 1 to the n over 3 to the n. Well, this is a little bit tricky. The negative 1 to the n is called an alternating piece, right? Because the only values it has, remember, n is just an integer. It's 1, 2, 3, 4. So this is negative 1 to the first, negative 1 to the second, third, fourth. That's just, that value is either a positive 1 or a negative 1. That's all it can be, a positive 1 or a negative 1. So the easiest way to do this is, let's treat this like two different problems. Let's do the limit as n goes to infinity. Let's do negative 1 to the n over 3 to the n plus n over 3 to the n. All right, well, we can simplify that second piece real quick. Let's leave this alone for right now. Plus 1/3. All right, so what's going to happen to this piece right here? Well, we already know what's going to happen to that. That's going to be 1/3. But what happens to this? Well, as n gets bigger and bigger and bigger, the top is either positive 1 or negative 1. Positive 1, negative 1, positive. But the bottom's getting bigger and bigger and bigger, like a billion, a trillion, a zillion, so on and so forth. So this value here, even though the top is bouncing back and forth between negative 1 and 1, that's heading towards 0, right? Because the bottom's growing and the top really isn't. So this goes to 1/3. So here we can say that our a sub n converges. All right, maybe one more here. Let's do another one with an alternating piece in it. What if I said a sub n is, let's do negative 1 to the n plus 1 all over 2. All right, now if we try the same thing that we just did, we're actually going to run into a little bit of a problem. We go n goes to infinity, negative 1 to the n plus 1 over 2. If we say, let's break that apart, because that looks like something we've done in the past, so that might be a good idea. Puts an n over 2 plus 1/2. Well, the problem is now we can't actually figure out what this value is here. This doesn't go away nice and easy like it did last time, because this value is either going to be a positive 1/2 or a negative 1/2. Positive 1/2, negative 1/2. So what you need to do, I'm going to put that's a question mark. I'm going to say, I don't know what that is. So let's actually just write out some terms in this sequence to see what happens. Well, if n is 1, let's start way back up here. If n is 1, negative 1 to the first is negative 1, so it's 0 over 2, which is 0. If n is 2, well, negative 1 squared is 1. 1 plus 1 is 2, divided by 2 is 1. If n is 3, that's negative 1 plus 1 is 0 over 2, which is 0. If n is 4, that's 1 plus 1, which is 2 over 2, which is 1. So if you notice, you can kind of see a pattern starting here, right? If n is even, that's a positive 1, so you get a 2 over 2, which is a 1. And if n is odd, that's a negative 1, so you get 0 over 2, which is 0. So this pattern keeps going forever. So the question is, does this converge or diverge? Well, here's where a lot of students get confused. You say, well, those values do fall between negative infinity and positive infinity. However, it's not a single value, right? This isn't heading towards 0, or it's not heading towards 1. It's bouncing back between these two. So here we'd actually say a sub n diverges. So this is kind of our second case for divergence. Our first was if it goes to an infinity, positive or negative infinity. The second one is if it doesn't actually equal a single value, right? That's kind of implied here. It says that that limit is a single value. Here, this limit is actually two different values. So therefore, that won't converge. It diverges. All right, let's take a look at just a little bit more vocabulary. Finish this section up. All right. let's see, A is okay, we're going to talk about something called monotonic. So a sequence is said to be monotonically, that's going to be kind of the first part. Let's do non-increasing. Now, what does non-increasing mean? Well, you kind of think about it as it's never increasing. So which means it's either going down or staying constant. So if you think about graphing your values, right? Here's your n axis and here's a sub n. So if n's 1, 2, 3, 4, non-increasing means it can do anything as one as long as it doesn't go up. So let's say we have a value here. So the next value can either be the same or it has to be smaller. It could be the same or smaller. So this would be monotonically non-increasing, right? It just can't increase. It can either be decreasing or the same. Now this will be true if a sub n plus 1, that will be our next term, is always what? Smaller than or equal to the one below it. Less than or equal to a sub n. So that's our definition for monotonically non-increasing, and monotonically non-decreasing, well, would be the same thing, just backwards, right? It either has to be increasing or staying constant. So generally we say that a sequence is monotonic basically if it is either non-increasing or non-decreasing. So you can kind of think about, here's an easy one. And you can just kind of tell by looking at this. If we had our a sub n is 1 over 2 to the n. If you think about that, excuse me, that sequence, that's 1/2, 1/4, 1/8, 1/16, 30 seconds, so on and so forth, right? So what is this sequence doing? Well, this one is actually just decreasing, would you agree? So technically, I don't know that all the textbooks go into this one. We could also say that this one is strictly decreasing, but we could say that what this is monotonically non-increasing, right? This is definitely not increasing. It's either decreasing or staying constant. So there we go. We can show that this is monotonic. The next definition that we need, because we're going to put these two definitions together here in a pretty important result, is something called bounded. Okay, a sequence is said to be, let's go, bounded above if a sub n is always less than or equal to some value. So bounded above means that there's some numerical value that the sequence never gets above. So if we take a look at this one is actually bounded above, right? The largest value the sequence ever has is 1/2. So this sequence here is bounded above by 1/2. We say that it is bounded below if a sub n is always greater than or equal to some value. So actually this one ends up being bounded below as well, because if you think about this, the smallest value this is ever going to be if we continue out to infinity would be 0, right? So this is actually bounded below by 0 because it can never go below 0. Okay, so a sequence is said to be bounded above if it's always smaller than some value, bounded below if it's always bigger than some value, and it's just said bounded if it is bounded above, and below. Okay, so if the sequence is bounded both above and below, then it's considered just bounded. So this actual sequence here has a maximum value of 1/2, it has a minimum value of 0, so this is a bounded sequence. A very easy example of one that's not completely bounded just our whole number, our natural numbers here, right? This is bounded below. The lowest value this possibly has is 1, but it's not bounded above, right? That thing goes out there to infinity. So that would not be bounded. This is only bounded below. This, since it's bounded above and below, would just be called a bounded sequence. Now, the reason that we want these two definitions is really just to write one kind of important sentence. Every bounded monotonic sequence converges. Every bounded monotonic sequence converges. Now notice I used the word monotonic, and I didn't say monotonically non-increasing or decreasing, because it can be either. Now remember, bounded, just by using the word bounded, means both bounded above and below. So let's take a look at, here's our n and a sub n. You can kind of see why this would have to happen. If it's bounded above, that means we have some value it never gets above, and if it's bounded below, we have another value that it never gets below. So you can kind of think about these two as a ceiling and a floor that you can never get outside of. So for each one of our n values, we're going to have an a sub n value. But since this thing is monotonic, means it's always kind of either heading up or staying constant, or heading down or staying constant. So just for the picture's sake, let's say that this is monotonically non-decreasing, which means it's not going down, it's either going up or staying constant. So if it's always going up or staying constant, you can say stay constant for a while, then it goes up, then it goes up. You can see, since it's bounded, eventually, either it's going to stay constant forever, which means that's what it converges to, or eventually it's going to run into that maximum value that we know it's bounded by, which means that would actually be what it converges to. All right, a sequence is just a list of numbers. You generally have a nth term formula or a generating formula for that. We had a couple different types, or a recursive formula. To tell whether or not a sequence converges or diverges, just take the limit as n goes to infinity. If that goes to a single value between negative infinity or positive infinity, we say it converges. If it bounces between values or heads off to infinity, we say that it diverges.